Alright guys, so today we're going to take a look at universal gravitation, and this is probably something that I imagine you guys would have seen probably last year, right? So what we're going to do today is just kind of dive back into it because it ends up being related to something that you've already done in circular motion, okay? So that's the connection that we're going to try and make today. So we'll develop the equation here, and then we'll apply it a couple times and talk about differences in how the equation affects answers, and then we'll apply it to circular motion, and that'll be it for today. Okay, so Newton's universal law of gravity, okay, states that every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses, right, and inversely proportional to the square of the distance, which we typically denote as radius. Okay, so what we'll see in the equation are squared. Okay, so proportional to, which means increases or decreases, right, by the same amount. So if I, or maybe by the same amount, but if I increase the force, it's directly proportional to the fact that we've increased the masses. Okay, and if we increase the distance between those masses, we decrease the force. Okay, that's what it means by inversely proportional. Okay, so what's the equation look like? Well, the force of gravity that we can feel will be equal to G, which is this gravitational constant that you see there, right? We're going to have this constant G multiplied by M1 multiplied by M2, the two masses that are experiencing the gravitational force, divided by the radius squared. Okay, and we can see over here that the gravity is going to be an attractive force, right? So if we have two masses, M1 and M2, they're going to feel a force of attraction between the two of them based on their masses and the gravitational force between them, right? So you can see the force 1 is having on 2 and the force 2 is having on 1 are both attractive, and they want to be pulled that way. Okay, and here you've got the radius or the distance between them. Okay, so that's the equation that you'll end up using. The units are as per usual in newtons, right, because it's force. And so we're just going to jump down here and have a look at some of the properties of the universal law of gravity. Okay, so this is an action at a distance force that's present between masses regardless of the medium that they're in, right? So it doesn't matter if it's in space where there is no atmosphere, if it's on Earth, or it doesn't matter. Water goes through whatever, rock, right? It's independent of the medium that you're in. And we see here, just mathematically, we're seeing the proportional statements, right, or improportional statements, right? So we're seeing the force is proportional to 1 over r squared. That indicates that it's inversely, because it's the inversely proportional, right? So if we increase the radius, we see a decrease in the force. Okay, and that's what it's put into words beside. We can see here if I increase one of the masses, I would end up increasing the force. Okay, F is an attractive force and only points towards the center of mass, right? Okay, so it always acts as like whatever the mass is, it's kind of like acts as a point mass, and it acts at the center of mass. Okay, so for example, we'll have a look at the first example here. We have two identical isolated particles, okay? And we want to ultimately find the gravitational force of one particle on the other. Okay? And so what we're going to have here is we can write out, well, you can draw a picture if you'd like. Each mass, so we have basically the same mass, right? They're 2 kilograms each. Right, and they're going to be separated by a distance of 30 centimeters, which you could switch into. Remember, we got to deal with meters, so just 0.3 meters. Okay. We want to find the magnitude of the gravitational force of one particle on the other. Okay, so what we're going to do here is we're just going to write out our law. So the force of gravity, remember we're just dealing with the magnitude, so we don't need the vector on top, okay, is going to be equal to G m1 m2 divided by r squared. Okay, and we're going to see this is going to be 6.67 times 10 to the negative 11, right? And that's going to be multiplied. Sorry, I should have said earlier too, the units on this gravitational is kind of a messy one, right? So dimensionally, it's messy from the standpoint that we have to get newtons out as an answer. So dimensionally, it has to make sense. Okay, so it's a little bit ugly from that standpoint. Okay, but it's a constant. Okay, and so we know that both these masses are going to be the same. So I'm just going to plug in 2 twice, which we know to be squared, right? So it's 2 squared divided by r squared, which in this case would be 0.3, and we square that. If we were to run through the calculation, we would end up seeing, I'll write it down, have the solution written, so 2.668, just for you guys to check if you're typing things in the calculator correctly, 10 to the negative 10 divided by 0.09, we should see a resultant force of 3.0 times 10 to the negative 9 newtons. Okay, so that'll be the force that each of those masses are experiencing, right? And it's the same force because both the masses are the same. They're just it's in opposite directions. Okay, it's an attractive force. Okay, so that's, I don't know, that's the application of that. We can take that and do things like what we were doing with the circular motion and forces in the centripetal acceleration, right? That's where we're going to go today. But one other thing I'd like to do is just illustrate to you, we can also apply this force, just like all the other forces, into situations where they might be acting at angles, right? And so what we're going to see here is what this question wants us to do. We have 3 different masses here, the 2, 4, and 6 kilogram masses, and what they've done is they've basically treated this here, the 4 kilogram mass, is sitting at the origin at 0, 0. Okay, and I think it also says in this question that the coordinates, we can just assume that they're in meters. Okay, so if I go up, I've gone up 3 meters, which means the distance between these two is going to be 3 meters. And over here, we're going to go 4 meters to the left. Okay, now this problem, the force that it's not going to be the magnitude of the force this time. We're actually going to have to solve for the resultant force that this 4 kilogram mass is going to experience. Okay, which means the resultant force, we're going to have some direction on here. Okay, it's not just going to be the magnitude of the force this time, right? Because the magnitude is great, but it doesn't tell us ultimately, like, we don't know where is it going to experience this force, right? Like, if I was to do F equals ma, which direction is this thing going to accelerate? So that's what the direction is going to do for us. Okay, so basically the same question for the start. Like, we have to find the magnitude of the force, right? That's you have to find that. So we want to find the resultant force on the 4 kilogram mass. Okay, so we want to find what is happening because of the presence of the 6 kilogram mass, and what's happening because of the presence of the 2 kilogram mass, right? Relative to the 4 kilogram mass. Okay, so we just want to see how is this mass here, the 2 kilogram, and how is the 6 kilogram affecting the 4 kilogram mass? That's how we're going to answer this question, okay, because that's what it's asking for. Calculate the resultant gravitational force on the 4 kilogram mass. Okay, so basically what's going to happen to this 4 kilogram mass? Okay, so what we need to do is we need to find the force that the 2 kilogram mass is having on the 4 kilogram mass. Okay, and we're going to see that. We're just going to apply GMM over R squared, right? So we're going to see G M1 M2 over R squared, which is going to be, we just start plugging in numbers, times 2 times 4, all divided by, what's the radius between the 2 and the 4? What's 3 meters? So 3 squared. And what you'll find is you'll find the force to be, when you type that all in, 5.93 times 10 to the negative 11 newtons. Okay, so that's the, remember this is an attractive force, and our point of interest is the 4 kilogram mass, right? So at the same time, oh, sorry, I put too many backs here, leave the newtons. Okay, so at the same time, so it's important that this mass, this 4 kilogram mass, we always kind of have like, there's an attractive force going towards the 2 kilogram mass, but at the same time, the 4 kilogram mass is also attracting the 2 kilogram mass, right? So I think what we want to do here is just kind of like, for simplicity's sake, is just assume that these two masses are going to be fixed, and we want to see what's going to happen here. So we're not going to see this movement of these two masses, okay? So we're just making a simple question here that just illustrates like, how is this 4 kilogram mass going to move in response to, or what's the net force that this 4 kilogram mass is experiencing based on the presence of these two other masses? Okay, assuming that these are not going to shift around. Okay, does that makes the question infinitely more difficult, right? So let's also take a look at the force that the 6 kilogram mass is exerting on the 4 kilogram mass, right? And you're just going to run through the same thing. You're going to go 6.67. Oops, don't forget the scientific notation. And that's going to be multiplied by the 6 times the 4, right? And what's the distance between those two masses? Well, it looks like it's 4. Okay. And so, if you were to plug that in, you would get an answer of 11.6 times 10 to the negative 11 newtons. Okay, so here are two answers. Okay, so we know the resultant force being exerted. Well, we're going to find the resultant force. We know two things here. We know kind of a y component, if you will, of the force being exerted, and we also kind of know an x component of the force being exerted, right? So keep in mind, though, the direction of these two forces, right? It's an attractive force. So the 4 kilogram mass is feeling attracted to, so it's in this direction, attracted to the 3 kilogram mass, sorry, the 2 kilogram mass, and it's also feeling attracted to the 6 kilogram mass. So you got two vectors here in nice fashion. How do we add vectors together? Well, we're going to add one this direction. This is going to be the this component, right? Because it's in the x direction, 6 on 4. So we're going to say 11.6 times 10 to the negative 11 newtons. And then we also have a y component, right? A force of attraction in the y direction. It's going to go up like this, right? And its component, it's the 5.93. Okay, and for you to find the resultant force that this 4 kilogram mass is experiencing, is going to be in this direction. And it's going to be at that direction. We need to find theta, right? Well, we know how to do this. Tan of theta has to equal opposite over adjacent. Well, we're going to see 5.93 times 10 to the negative 11 divided by 11.6 times 10 to the negative 11. And you should, if you run through this, you'll find that theta will equal 31 degrees. Okay, so to finish off this question, I just have to buy myself some room here. Finish off this question. We just write the resultant force. Oh, we have one more step to do. Sorry, didn't finish. We have to find the actual F net here, which you guys know how to do. Nothing too crazy, right? We have to find F net squared has to equal the sum of the two squared pieces on the side as well. Okay, I think I may have, I think I may have written the wrong number down here. Sorry. So when you guys actually type this in your calculator, sorry, just ahead one step. 11.6 times 10 to the negative 11 is the resultant force. I just had it a line below. I wrote it wrong. So it should be negative 10.0 times 10 to the negative 11 newtons, okay? The resultant force, after you find F net squared, from, it'll be the square root of x squared plus y squared, right? You should see 11.6, that's where this number came from, times 10 to the negative 11 newtons, okay? That's F net. So your F net as a force vector, right, is going to be 11.6 times 10 to the negative 11 newtons. Which direction are we headed initially? Well, we could say in the west direction, right? And if we're looking at our diagram, I suppose too, we're heading in the west direction, and then we're going to go north, okay? North how much? 31 degrees north. Okay, and that's the resultant vector that you're going to have for this particular question. Okay, that's your answer. Okay, so, no, like it's just a force, guys. It's just a force, and it's a different kind of force, right? And you can use it in different situations where we're dealing with, you know, if we're looking for the gravitational force between two massive objects, or even little objects too, right? You can see the little objects, how small of a force that actually is, though. It's a very small in terms of magnitude, very small force. You know, a force between Earth and the Sun is much, much larger because the masses are so much larger, right? So we're just going to have a look at that now. So from the standpoint of proportionality, right, what happens to the force of gravity when one mass is doubled? Well, let's see what happens, right? So we'll say force 1 is equal to g of m1 m2 over r squared originally, right? This is just the original equation. And we want to know what happens if I double one of the masses. Well, let's see. F, I don't know why I have a 2 there. Should be r squared, sorry. So what happens to the force? We'll call it, sorry, F2 will be, a new force, will be equal to G M1, M2, M2, let's say, 2 M2, right? We're going to double it, divided by R squared, right? Well, it looks like it just doubles the amount of force, right? Everything else hasn't changed. Nothing else has changed, right? Like G is still there, M is still there, M is still there, right? R squared is R squared. The only thing that's been added, right, is this factor of 2, right? So we know that the new force is going to be doubled, right, because of this 2. But what happens to the force of gravity if the distance between the two objects is doubled? Well, that's a different scenario. Let's do it again. So we're going to have an initial force again, Gm1 m2 over r squared. That's our original force. What happens when we double the radius? Well, we're going to see Gm1, Gm2 over 2r squared, right? We're going to double the radius and then still square it. Well, if I were to distribute that squared in, I'm going to see Gm1 m2 over 4r squared. Well, let's have a look again now, right? Here's the original. We've still got all these constants in here, but now we have this addition of this 4, right? So what happens when we double the amount of distance between the two objects? We decrease the force by 1/4, or we cut it in half, right? Or not half. Cut it into a quarter of the strength. That's what we're going to experience now. Okay, so we're going to have 1/4 of the strength there now. Okay, but what happens if the force of gravity, when the distance between the two objects is cut in half? Well, let's see what happens, right? So if we're going to move the two objects closer together, right? Well, same thing. What's the new force going to look like? Well, we're going to see Gm1m2 over 1/4 r. Oh, not 1/4, 1/2, sorry. 1/2 r squared. Same thing. We're going to see Gm1m2 divided by, now what's going to happen? We'll get 1 over 4 r squared. Well, you guys know when we deal with fractions inside of fractions, right? You're going to bring this up. Right, this is over 1, basically. So to deal with this 1/4 is your question, like how do I deal with this? Well, when you have fractions inside of fractions, you can bring it up and multiply by the reciprocal, right? And so we're going to have Gm1m2 divided by r squared, but multiplied by 4 over 1. This is the reciprocal of 1/4. Okay, so we can see that force quadruples. Oh, I don't know how to I don't know if that's right or not. Quadruples. Something like that. I don't know. Anyway, it's 4 times as big. Okay. Now let's suppose the two objects attract each other with a gravitational force of 16 units. Okay. If the mass of both objects was tripled and the distance between the two objects was doubled, what would be the new force of attraction between the two objects? Now, I think earlier this week we talked about questions that would exist like this, right? Where you have to extract, like at university, you know, they'll give you a hypothetical situation like this and you have to be able to apply it to the correct equation. And what they'll do is they put all these different answers down here and you have to select which one you want is correct, right? So they don't give you any numbers. They just hypothetically what would happen in this instance, right? Well, let's take a look, right? So we know that, you know, we're dealing with our force of gravity equation, Gm1m2 over r squared. We're dealing with this equation, obviously, because that's where we're at. But in the test, you might not know that, right? But you know the gravitational force that would prompt you to this equation, right? We know that it's 16 units. So I'm just going to say, okay, well, 16 has to equal to Gm1m2 over r squared. Now the question now becomes, what happens if the mass of both objects was tripled? Okay, so let's do that now. So 16 equals G 3m1 times 3m2, and the distance between the two objects was doubled. Okay, so we're going to say 2r squared. Okay, so the question becomes, okay, well let's simplify this and collect all these coefficients and see what happens. Okay, so we're going to see 16 should equal G times 9m1m2 over 4r squared. Okay, so this new force, like what's going to happen? Overall, you're asking yourself, what's going to happen here, right? Well, okay, well, let's extract the coefficients that are here. We're going to see 16 should equal 9 over 4. Gm1m2 over r squared, right? So you're just trying to get the original back and extract what's changed. That's what we've done with all these proportional statements, right? Now you can say, okay, well, you know, like what's going to happen to the actual force? Well, F2, the new force, is going to be equal to the original force, which we knew as being 16, right? So what you're going to do is you're going to take this 16. It was this. Well, where else does this appear? It appears right here. So this new force, what the new force is going to be 9 over 4 multiplied by the 16, which will be 36 newtons. Okay. So we have this heavy thinking idea, right? So we were like, okay, well, we just discussed what would happen if we tripled the masses, right? And along those lines, if we think about something that actually exists, right? Like we're comparing the mass and size data for the planets of Earth and Jupiter, we observe that Jupiter is about 300 times more massive than Earth, okay? So we might quickly conclude that an object on the surface of Jupiter would weigh 300 times more than on the surface of Earth, okay? So for instance, one might expect a person who weighs 500 newtons on Earth to weigh 150,000 newtons on the surface of Jupiter, okay? But we don't see that this is the case, right? In reality, we see that a 500 Newton person on Earth weighs about 1,500 newtons on the surface of Jupiter, okay? What we want to do is we want to, like, how could this be, right? Because we just looked at the fact that, like, what would happen if I increase the mass with 300 times? You would see that that's directly proportional, right? Like we would see, we already said the force of gravity that we experience is proportional to the masses, right? And so if we multiply those things by 300, we should expect to see the force of gravity go up by 300, but we don't see that. But we also said something else. The force of gravity is inversely proportional to 1 over r squared. Okay, so these two things in combination with one another, as we saw up here in this question, go hand in hand, right? So let's draw a little picture out here, right? So we're going to have Earth with some radius, but then we're going to have Jupiter. Okay, the much larger radius of Jupiter mitigates the effect of its 300 times heavier mass. Okay, so you guys got to keep in mind if you're looking at, and we could do this with any equation that we've experienced so far in the course, like what would happen if, and you can kind of conceptually, like if F equals ma, right? If we doubled the acceleration, what would have happened to the force, right? What would the force had to have been in order to create that double, right? Well, those are two proportional statements, right? So if I double the force, I double the acceleration. Okay, we can do this with anything, and that's what they like to do at university sometimes. Okay, so in the last stretch here, okay, we just want to revisit this idea of uniform circular motion and gravitation, right? So let's think about a satellite orbiting Earth, right? Why doesn't, like, we talked about, like, the reasoning, like if somebody was on a merry-go-round, right? The reasoning why, like, they don't just go flying off is because we have this centripetal acceleration forcing us towards the middle all the time, in combination with the force of friction, right? And so here we're going to experience the same thing here, right? This little red arrow, this is the force of gravity, right? And it's keeping it like pulled inward, right? But this pull here is being balanced by the velocity at which this is moving, WV, right? The speed, right? Tangential speed. So if we were to write, again, we're just going to write the centrifugal or centripetal force. That's going to equal to ma, the centripetal acceleration, right? And we know it's pointing inward. And we learned that the centripetal acceleration was equal to v squared over r. In this case, our centripetal force that's keeping us in circular motion is gm1 m2 over r squared. That has to equal m, and it could be m of the object that's moving, could be m1. Okay, we'll label that m1. Okay, what ends up happening, if I were to try and solve for, like, our question is, like, how fast is this thing moving? Or, like, how does it stay in orbit, right? Like, we need a certain like velocity. So that's our point of interest, is like I want to solve for, well, what is this velocity, right? Well, M1s are going to cancel, right? Probably the mass of the satellite, right? The smaller of the two. M2 would be the mass of the Earth, right? I should have maybe like labeled it like that, right? But it is what it is. We'll go like this. Okay, so the mass of the Earth. So the mass of the satellites cancel out. Now, something else also happens if I'm isolating. If I were to multiply both sides by r, right, the radius is the radius. So if I multiply both sides by r, I'm going to see a canceling of one of the r's in that equation, right? So it turns out that the velocity that these things are moving, or that the satellite's moving, not these things, is going to be equal to the square root of g multiplied by the mass of the Earth divided by the radius. Okay, I find the thing that's most interesting is that it's kind of independent of whatever it is that's orbiting Earth, right? There's no mass. There's no mass there. It's not taking that into consideration at all, right? And so we call this is like a general rule, because it applies to all objects, because, you know, the mass is canceled. It doesn't matter what it is you're working with, right? And so we call this V escape. And it's the velocity that you need to attain in order to escape the force of gravity that the Earth has on you, right? So if you have a velocity greater than this, then you're able to escape, right? You get out of orbit. Okay. So example 3 just wants us to look at calculating the actual gravitational attraction between Earth and a 70 kilogram student, okay, standing on a plane that is 12,000 meters above the Earth's surface. Okay. So we know the mass of the Earth is 5.97. You guys would always be given this, times 10 to the 24. As you do more physics, you come to learn some of these like constants like the back of your hand. The radius of the Earth, you guys will also be given 6.37 times 10 to the 6 kilograms. It's meters, not kilograms. And then G, the gravitational constant, you also know. Okay, and it's got all those ugly units. Newton, meters second, or meters squared, kilograms squared, or whatever it is. Am I right? Yeah, I'm right. Okay, meters squared over kilograms squared. Okay, so we're just going to apply our equation again. The force of gravity that I'm experiencing now, the interesting part to this question is we try to throw oh, where did I get the 12? Ignore this for now. This changes the question. Okay, we're assuming that they're on I don't know where this question came from. Oh, I know. Sorry. Never mind. I have it. So whenever you're given a radius like this, right, the radius has to be wherever you are in the air plus the radius of the Earth. Sorry, guys. Okay, you got it figured out though. So we have the radius of the Earth, that's this number, but then the student is an additional 12,000 meters above the Earth's surface, right? So the radius for this particular question, this caught me off guard, right? we're going to have the original 6.37 times 10 to the 6, right? That's this piece here of Earth, like right to the surface. But then they're in a plane flying above the Earth's surface, right? 12,000 meters. Okay, if you were to do the math on all that, you just type it into the calculator, you're going to see that the force, 684 newtons, that's the force of gravity that this student, 70 kilogram student, is experiencing based on the force of gravity, right? And being 12,000 meters in the air. Okay. The last question here. Okay. And if I ever ask you about a particular, I have to give you the information for that, right? So we know, G is always G. It's always 6.67 times 10 to the negative 11 with all the funny units. We know the mass of the moon is 7.35 times 10 to the 22 kilograms. And I know that the radius of the moon is 6 meters. Okay. So I see the word acceleration. Okay. So I'm seeing, okay, well, let's say or not even essential. It's not rotating. Sorry. It's just F equals ma. Okay. What force are we dealing with? We're dealing with G m1 m2 over r squared. Right. That has to be equal to the mass of the object, right? Because that's the thing actually accelerating. We'll call it m1 multiplied by a, the acceleration that it's experiencing, right? Well, m1's cancel, and so the acceleration is just equal to g multiplied by the mass of the moon divided by the radius of the moon squared. Right? If you were to type all these numbers into there, you'll see that the acceleration that this object is experiencing would be 2 meters per second. Okay, guys, so that's the law of, universal gravitation, right? Which I believe you guys would have seen that equation last year. Okay, you would have looked at like force diagrams, but like this question up here, the one we did. Okay, what we did, we just kind of recapped it today. Made sure that everything was okay, and we took it and we're going to apply it to circular motion questions. And in particular, we call these things. There was a famous physicist named Kepler, right? And he looked at like orbits and how objects orbited other planets, right? And the gravitational force that they exert on one another, and ended up coming with Kepler's laws, right? Which I don't think we're going to have time to get into in this course, but you guys will probably see if you take astrophysics or astronomy or something at university, you'll get into Kepler's laws. Okay, they all kind of find their foundation in this gravitational force. Okay, so that's it. You guys let me know if you have any questions. I'll assign some, well, there's homework questions posted, and I think I've actually picked out which ones you need to do as well. Okay, so just let me know if you have any questions with all this.